acceleration. And the definition of acceleration is it's telling us about how quickly velocity changes. By the way, everything that you're going to see in the PLC, I've covered now. It was this last graphing piece that really needed to be there for the PLC. So let's go talk about this. So we're talking about how quickly velocity changes. So the thing that we want to focus on is that there's a problem with language. In physics, anytime someone says or states acceleration, it means velocity change. But that's not everyday language, right? Because if you're driving a car and you're speeding up, everyday language, when you're saying that you're speeding up, we say the word accelerate, right? You accelerate. But if you're slowing down, do you say you accelerate? But in physics, we do. Acceleration is a general definition. Everyday language is not the same as physics language. And so what you're going to find here is that everyday language, they say decelerate, but in physics, that's not the way it is. So right away, there's going to be a problem. Okay. And what you're going to find here is that when we say the word speed up, what we really mean in physics, we say positive acceleration. If we're slowing down, we say negative acceleration. So the only difference between speeding up and slowing down is the sign of the acceleration relative to the velocity here. So what we want to do now is that we want to go in and we want to sort of start talking about acceleration. Well, acceleration is a vector. What do I mean by that? That means when I write acceleration, it's one of these quantities that has the arrow. But as soon as we say that it's an arrow type thing, that means it has magnitude and it has direction. So I got to talk about both of these in order to talk about acceleration. Okay, so let's talk about the magnitude of the acceleration. Acceleration is how quickly velocity is changed. So if I was to just say a simple definition, we say that acceleration is how quickly velocity changes. And so mathematically, the way we write it here is that we say, yeah, acceleration then is the change in velocity divided by the time interval of change. And so when I'm looking at this thing, if I'm talking about the magnitude, then the magnitude of A is, we call that A, and it's literally this guy without any change, without any sign. So when we write acceleration, we write it like this, or if we're talking about the magnitude, we write it just like that. So the length of the vector is given by this quantity. So remember, this is the length of the acceleration vector. Okay, so if that's the case here, let's physically interpret what we mean by acceleration. Okay, so I want to do a physical interpretation. You are all experts at acceleration. Of course you know it, right? You know that if you're stopping a car, what happens to your body? If you're stopping a car, you know that your body moves forward. It's almost like somebody is pushing you. Nobody's pushing you, right? If you're in your car by yourself and you're braking, is somebody behind you pushing on you? Of course not. But a lot of times people say, oh yeah, I got pushed forward. That's a bunch of BS. That's a frame problem. And then, of course, if you're speeding up, you know that your body in this case, what does it do? It moves backwards. Okay, so if it's moving backwards, what do I mean by that here? As far as the physics is concerned, the strength and the magnitude of the acceleration is measured by the strength of your body's motion. So the strength, right? What I mean by strength, I really mean magnitude. So the strength / magnitude of the acceleration is a measure, right? It's a measure of the, how do I say this? Of the strength of your body's motion. I'm sure there's a much better way to put this, but that's what's coming at the top of my head. The magnitude of the acceleration is a measure of how the strength of your body to want to keep moving forward or to want to go backwards. And what I mean by this here is that, look what happens. So if you stop slowly, what does that mean? If you stop slowly, what you find here is that your body slightly moves forward. Right? If you just hit the brakes really light, what happens? Your body slightly moves forward. Because your body moves slightly, that means the measure of the acceleration then tells you that it's a small acceleration. That's what I mean by your body's strength. However, what happens if you stop quickly, right? If you slam the brakes on, your body, what does it do? Your body sort of like flies in the forward direction, right? You just go, and if you're going fast enough, man, you could go right through your windshield. So in this case here, because your body is reacting to that kind of a strength, you now have a large acceleration. So think about this in terms of the equation now. In each situation, let's say that your speed change is exactly the same. So that means if you're driving 35 miles an hour and you suddenly stop, your final speed is 0. So your change in speed is 35 miles an hour no matter what. But wait a minute. If you're lightly pushing the brakes, what's actually happening? The big thing here is that you're doing this over a larger time interval. But wait a minute, if you really stop really quickly, you're stopping in a very small time interval, so that time interval is tiny. So what happens? That time determines how big the acceleration is. And so if I look at this thing in a more physical way here, right? If I draw a picture here, God, where's my mouse at? I mean, you could imagine that you're driving a car, right? Here we go. So a good situation would be, here's you in a car, right? You're driving the car, and here's you, right? You got your arm out of the car, and how fast are you moving? You're moving 35 miles an hour, right? And what you're seeing here, all the way over here, you see a stop sign, right? There's your red stop sign right there. So the question is, as you're driving your car, I'm assuming that if you're going 35 miles an hour and there's no cars in front of you, you're going to stop your car by probably putting on the brake, nice and light, so you're not like putting on at the last moment here. So in this case here, what we're saying here is that as you are you're going to brake here, you're going to brake over a long period. So you're going to brake over a long period. Now, imagine the same scenario now. Imagine that you have the same situation, right? You're still going 35 miles an hour. And yes, you're approaching the stop sign up here. But this time, something happens. What happens this time? A little kid runs out in front of you in the street. I'm assuming that you're not going to push on the accelerator. I'm assuming that you're going to hit the brake. So in this picture here, what are you actually doing? In this picture, you're braking over a short time interval. So if I look at this time interval here, this guy's going to be really small. This guy's going to be really big. But when you look at the change in velocity, the change in velocity in both cases is going to be 0 minus 35 miles per hour. So this is a constant change in velocity. So if I look at my change in velocity, then you could see that in both cases, the velocity is exactly the same. The change in velocity is exactly the same. What's the big difference? One has a big interval, one has a small interval. So what happens? This guy is tiny, this guy is huge. So in this case here, we then say that this is a large acceleration. This is a small acceleration. That's what I mean by the magnitude of the acceleration. Your body tells you how that is. What you're seeing here is that I have a review of what we were doing last time. Here, I always think I'm organized. There's all these little details. So we started talking about acceleration. Now, acceleration is really easy to mix up with velocity. So a word of caution, velocity and acceleration are not the same thing. Acceleration implies that you have changed velocity. So there's two ways to change velocity. You can change the speed while holding the direction constant, or you could keep the speed constant and then change the direction. This latter one, we're not going to do until chapter 6, so I'm just going to ignore that. So if I change speed, the only way I can change speed here is if I speed up or slow down. Remember, acceleration is a vector, so we have to talk about both magnitude and direction. So we started talking about the magnitude of the direction of the acceleration. So let's go look at that. And what we said is that the magnitude of the acceleration is how quickly velocity changes. In other words, mathematically, the way we write this is we say that the acceleration vector A, and we take the magnitude of it. That's what we mean by those vertical things. And then we drop all that nonsense, and then we just call it A. And then that's the change in velocity over the time interval that we're looking at. So the way to physically interpret what acceleration is, if it's about how quickly it changes velocity, just pay attention to when you're either speeding up or slowing down. If you're stopping while driving or slowing down, your body moves forward. That tells you that you're accelerating. If you're speeding up, your body moves backwards. That's telling you that you're accelerating. Now remember, in everyday language, speeding up, we typically say acceleration. Slowing down, we say deceleration. But in physics, we don't keep that language. It's all about the sign of the acceleration that tells us whether we're speeding up or slowing down. Now, the strength of the acceleration is a measure of your strength of your body's motion. Is there a better way to say this? I'm pretty sure there is. I couldn't figure it out. But here's what it goes here. This is what I mean by the strength of your body's motion. If you stop slowly, what I mean by slowly, that means over a very long period of time. So that means you're braking very lightly. Your body slightly moves forward. Its strength to want to go forward is not so strong. So that's a small acceleration. Why? You're not changing your velocity very quickly. On the other hand, if you stop really quickly, the strength of your body to go forward is very strong. That's what we call large acceleration. That's what I mean about your body's motion. The strength of your body's motion is directly proportional to the acceleration. And so what you're seeing here is that I tried to give you this example about driving. So you're driving your car at 35 miles an hour. And what you're finding here is that you have a long braking distance. So you start braking over a long distance. When you do that, because it's a long distance, it's taking you a lot longer to come to a stop. So when you're feeling your body's motion is very small. As a consequence, your acceleration is small, right? You have a small acceleration. Why? Because the time interval that you change your velocity is large. Then we talked about our other case here. You could imagine if I had the same car and all of a sudden a small boy runs out in front of the car because you weren't expecting this small boy. Your braking distance is much shorter. In other words, you have to stop much faster. When you look at that, when you feel your body's motion in purple here is much stronger than it was in light blue here. So that immediately tells you that you had a big acceleration, right? You have a large acceleration. Why is it large? Because you stopped over a much shorter time interval. And that's really what the magnitude of the acceleration is. So then we just started talking about the direction of the acceleration. And the direction of the acceleration is opposite to your body's motion. So here we go. So if you're stopping, we know that our body's motion is in the forward direction. So our acceleration must be in the opposite direction. This is what we call negative acceleration. So negative acceleration implies you are slowing down. So you could see that the velocity and the acceleration are in opposite directions. But if you're speeding up, you feel your body being pressed into the seat. And because your body's being pressed into the seat, the acceleration is opposite the direction of your body's motion. So therefore, this is what we call positive acceleration. So even though in everyday language we talk about positive, we could talk about acceleration in physics. We say that's positive acceleration. What do I mean by positive acceleration? The velocity and the acceleration are in the same direction. When we're talking about deceleration in everyday language, and think about vectors, you'll see why that makes more sense. Well, I said vectors, but graphically. So I just got a message that says that my internet's a little bit unstable. So hopefully I'm not freezing. And by the way, if for some reason I just go blank because of an internet connection, note, I'm not just like saying, hey, I'm going to cut class short early today here. Believe me, I'm trying my best to get back into the class. And if you could just hold on, I'd really appreciate that. And just wait till I somehow get reconnected again. So now to talk about the magnitude of the acceleration, I really got to talk about the units of the acceleration. So suppose a car has a uniform or constant acceleration. By the way, in this course, that's always the case until we start looking at something called conservation of energy or something similar to that, okay? Now, what you're finding here is that if I do that, what we find is we find the following thing here. That delta V tells us by how much the velocity has changed, and delta T tells us about the time interval in which the velocity change of 5 meters per second every 1 second, then that 5 meters per second tells me how much the speed changes per every 1 second. So suppose that at 0 seconds, I have a car that's moving at 10 meters per second. Well, if I have acceleration pointed in the same direction as the velocity, which is in red, and the acceleration is in green, then that means from 0 to 1 second, I changed my speed by how much? 5 meters a second. So you could see that I increased it by 5 meters a second. So I go from 10 to 15. And then at 15 meters a second, if I continue to accelerate, then that means I'm going to change my speed from 15 to 10 meters a second. And so it's going to continue to change here by this constant amount. Okay, apparently my voice is going in and out. I don't know what to tell you. Hopefully it's not too bad, and I apologize.
I can hear you fine. So I don't know about everybody else, but I can hear you fine.
Okay, thank you. I'm hoping it's not me. So let's just leave it at that. And if I keep moving along the same example, you could see that at every interval from here to here, 15 minus 10, from here to here, 20 minus 15, from here to here, 25 minus 20. You could see that I'm constantly changing by 5 meters a second. That is an acceleration. See that this acceleration is 10 meters per second. So the magnitude of this acceleration when I'm slowing down here is larger. Now, because it's larger, what this tells me here is that that I'm going to be changing my velocity even more. So if I look at here, I start off at 10 meters, 15 meters a second. And if I'm slowing down, the acceleration, because it's in the opposite, is reducing the speed. So you could see here that when I look at this interval from here to here,
I'm going from 40 to 50, which is minus 10 meters a second. And that's what that negative acceleration is doing. And if I go from here to here, you could see then I'm going from 30 to 40, which is minus 10 meters per second. So that acceleration keeps telling us by how much the velocity is changing. Okay, so now let's go look at this thing here. And so what I want to do here is that I want to go in and I want to then look at this thing graphically because I think there's a lot of information here. So let's look at that. So to do this, to get a real understanding of the velocity, I want to plot velocity versus time. And we kind of done this already with position, but check this out. I can write this, and if you follow what we did last time, I can replace the velocity and set one of the times equal to 0. So what this is really telling me here is that I can write V2 equals to V1 plus AT, but because we know that we have positive and negative velocity, I can write a plus or minus sign right here. So our sign convention that we've already talked about here, right? Tells me this. If A and B point in the same direction, then acceleration is positive, right? And I could say just the opposite for the other case here, right? If A here point in the opposite direction, then acceleration is negative. So what do I mean by that? Well, if I plot velocity here, and I move at a constant velocity, this line here represents V equal to a constant, and it will not change. However, if I'm speeding up here, then I know that I have this term here, and now I have a positive sign here. So what does that mean? If I start off at some velocity, V1, and I go to a higher velocity, V2, over some time interval, then that means when I move from here to there, right? So if I come over here and I plot this thing here, if I move along a linear line, what you're seeing here is that I went to a higher acceleration. And the reason why I went to a higher acceleration is that there was a height change of what? AT. It increased it by a positive value right here. And that's what that AT value is. So where V2 is greater than V1, that's what we mean by speeding up. It's that AT term that actually does that. On the other hand, if I'm talking about slowing down, what you're seeing here is that I still have my line of constant velocity not changing, and maybe this is my initial speed here, V1. Now, if I have an acceleration that's in the opposite direction, where I'm talking about slowing down, then we know that the big difference between these two is that negative acceleration. That has to have a negative. So if I have negative, we then know that V1 is then larger than V2. So if I come down and I plot this thing here, what you're seeing here is that I could then move to a lower velocity. And what's getting me to go up and down here is this minus AT, or up here, that was positive AT. And so that acceleration graphically makes sense when we talk about positive and negative acceleration. Okay, so I am now done with this chapter here. And I'm gonna go on to the next chapter to actually try to, make sense of all this concepts. So here, let me just say this, that chapter 1 is about the concepts of motion. So now I want to take these concepts of motion and I want to go into looking at the kinematics. The kinematics branch of motion is the mathematics of